everybody. Mobile app performance has an important impact on user attention. But what are the issues that could make a user unhappy? How does it look a user nightmare? Personally, I have identified two main issues that could define a user's nightmare. The first one is a fast draining battery, and the second one is a device running out of memory. The research shows that 53% of all the users uninstalled or remove a mobile app with several issues like crashes, freezes, or errors. And 36% of users stop to use a mobile app if due to the heavy battery usage. My presentation will focus on WorkManager, which is a library responsible to manage the background work. It was released at Google I/O 2018 and is part of the Android Jetpack. But before I will talk about the WorkManager, I think it's important to have a better basis about a better understanding about the Android memory model. After that, we will make a short review about the current background processing solutions, and we will see where the WorkManager is added in that schema. And finally, we will talk more about what WorkManager it is and what are the main entities of it and how they could be used. And at the end, we will make a short recap about the concepts that we have learned. So why should we, the Android developers, focus on understanding what's happening with the memory on a device? As an Android developer, I learned that when I build an app, it's not about me, it's about the users who will interact with that app that I build. So it's important to take care about the memory usage. Because Android is for everyone. So we have an ecosystem, an entire ecosystem. And when I talk about this Android ecosystem, I'm talking about the apps, the devices, and the users who use those devices. So our focus should be on all these kind of the devices. The devices could be split in three main categories based on their configurations. We have the entry-level devices, we have the mid-range devices, and the premium devices. When we talk about the memory availability and usage, for sure we should focus on the entry-level devices because the other ones have enough memory to use. So, if we are not able to build mobile apps that work properly on the entry-level devices, those devices will stop to be produced by the companies, and a big part of our users will disappear. This is not a good thing. Those users will be disappointed, so we don't want to get these kind of things. But on a device, the physical memory is split in pages. A page has about 4 kilobytes. And these pages are split in three main categories. There are the used pages, the cache pages, and the free pages. The used pages represent actually the memory that is currently used. The cache pages represent the memory that is backed by the device storage, and those pages could be reclaimed if they are needed. And the free pages represent actually the memory that is free right now, that is available to be used. Let's take, for example, a device with 2 GB of RAM memory. And let's put it under memory pressure. At the beginning, we have enough free memory, we have also some cached pages, and we have some used memory. So we have right now a happy device. Our apps work well, so everything is okay. After a period of time, we continue to use the device, we continue to open other apps and reuse the previous ones, and so on. So the device is under the memory pressure. What happens right now? At this moment, the Linux kernel will call the kswapd, which is a mechanism that is responsible to get some more free memory. And the only solution that it has is to go to get the cached pages and reclaim them. This process could take some time, and maybe that action will be also visible for the user. The apps start to be a little bit freezed. Okay, we continue to use the device, we put it again on the memory pressure, we open new apps and so on, and because we don't have so much free memory, we end up by not having any more free memory, and at that moment, the low memory killer is launched. What does this mechanism? It is used in order to kill the processes that use the memory. This could be a good thing for the memory, but it could be a bad thing for the user, because at the moment, this low memory killer could decide to kill the app that the user is using right now. In order to understand how this low memory killer works, it's important to see what are the processes available on an Android device. And there is an entire list. I will start from the top. First of all, we have the native processes. And here we have the init, kswapd that you already discussed about it, daemons like netd or logd or Android device bridge, and so on. There is an entire list. After that, we have the system server. System server is responsible to keep that list available. Then we have the persistent processes, like phone calls, the possibility to have signal, to have Wi-Fi, to have a Bluetooth connection. The next process list is represented by the foreground apps. Let's say that our user right now is trying to use the Android Makers app. He or she wants to see what's happening today, what is the agenda, more details about the speakers. In the same time, the user is listening some music. So that process, it's part of the perceptible processes list. So the music sound, it's listening in the background. The next process list is represented by the services. It is possible that at this moment on the device to have some background services that synchronize the data between the app and the server, or maybe back up some files or images to the server. We have also home app with a wallpaper. I think a big part of us changed the default wallpaper of the device. After that, we have the previous app that was used by the user. Maybe it was Google Maps in order to arrive here, or another app, and some cached apps that were saved by the system and they were previously used. Okay. So at the beginning, like we already saw, we have some free memories. We get the same example with the device with 2 GB memory. And the device and the users are happy. After we put the device under memory pressure, we will go to that moment when the low memory killer appears and start to kill the processes. And in this moment, the low memory killer will start to delete and remove the processes from bottom to up. So first of all, it will remove the cached apps. If it is not enough, it will continue with the previous app, and it will also destroy the home app, which will make our paper to disappear. So at that moment, the user will see that his paper or her paper, wallpaper doesn't appear on the device. If it's still not enough, it goes to the services and perceptible processes, and the music will stop because it will kill the background service that was responsible to play the music. And if it's still not enough, it will go and it will kill the mobile app, the foreground app, the Android Makers. And in this moment, for sure, we have a very sad user because he's not able to check the app. And if it's still not enough, the low memory killer will go up and will start the system, and your device will be rebooted. And at this moment, for sure, you have an angry user. So this is important to take care about how we manage the memory on an Android device. In terms of Android battery optimizations, in the latest releases, Google launched many features in order to improve the life of the battery. In the Android Marshmallow, they released the dose mode, deep dose mode, and app standby. What does it mean, deep dose mode? It represents the fact that when the device is not used and is not moved, it will go to a deep sleep, and all the background work will be cut. So in this case, the life of the battery will be longer. On the Android 7, they released Dose on the Go. It's an extension of the deep dose, but it's a lighter version of sleep. I mean, the device, it could be also moved, but it has the screen off. And in that moment, just wake up at some time the system in order to check if there are some jobs that should be run. After that, on Android Oreo, they launched the background service limitations, and in Android Pie, they launched app standby buckets. And this app standby buckets, it's actually an extension of app standby from Marshmallow. And this thing represents the fact that the apps are split in 4 main buckets: active, working set, frequent, and rare. And based on that, the allocation of the memory and of the battery is done using some machine learning algorithms. Okay, so we covered the part with the Android memory model and the battery optimization. Let's go to talk about the background processing solutions. Over the years, Google launched different background processing solutions. For example, we could use the job scheduler, but it's important to know that it works only for API 21+. Also, if we have Google Play services, we could use Firebase Job Dispatcher, which is backward compatibility, but if we want to launch our app in China, it will not be a good decision. Another option that could be used is the Alarm Manager with the broadcast receiver, which is also backward compatibility, but the issue is that the broadcast receivers will be the subject of the latest updates from the Android Pie. So when we try to select a background processing solution, we have 2 main options. The first one is to exclude the entry-level devices, and we saw the result. And the other one is to spend a lot of time and build something from scratch. Another way that could be used in order to define what solution to use when we have some background work is to use this schema of splitting the services, the background solutions, in based on 2 main categories, based on time and also based on the execution time, the importance of the execution. And for example, if we want to run a service that should be done when the app is active, we could use the foreground service. If we are more on the best effort area, we could use the thread pool, coroutines, or RxJava. But it appears also the case when we want that our our task to be run later. I mean, it's not important to be run right now, but we need to make sure that that task will be run, even if our app or system will restart. And in this case, we could use a job scheduler, but don't forget about the fact that it works only for latest APIs, the job dispatcher, but we'll need Google Play services, or Alarm Manager and broadcast receivers. WorkManager is in this category. So, WorkManager is a library for managing deferrable and guaranteed background work. What do I mean by deferrable? It represents the fact that it's not so important for us that this task should be run right now, and we could run it later. For example, if we want to upload some logs to the server, we could do it also later. It's not so important to be that this task should be done right now. And guarantee, it means that it should be done no matter what. I mean, even if our device will be restarted or our app will be closed, that task should be done, because we are, in this case, with the logs, it's important for us to know all the time what's happening with our app. Why to use WorkManager? There are a lot of advantages. We have backward compatibility. It works for API level 14+, and it is not necessary to have Google Play services. Also, it follows the best practices, supports one-off and periodic task. We are able also to chain the task, and also we are able to define some constraints on which this task should be done. And finally, we are able to make sure that our task will be executed no matter what. When to use the WorkManager? WorkManager is not a general solution for all the background processing part. So it has some specific scenarios on which it could be used. For example, if we want to fetch the data periodically, a good example could be when we want to send the user's location to the server at a period of time. Another example could be to upload images and files to a server. or to sync the data between the app and the server, or sending logs to a server. And also another example could be to use WorkManager when we execute expensive operations on data. And a good example here could be to have some images on which we should apply some filters, compress them, and after that upload them to a server. Okay, in order to use WorkManager, we need to define the dependencies on the Gradle file. The current version is 1.0.0 alpha 10, and I used Work Runtime KTX version. The alpha version was released the past year on May in 2018. The beta version was released in December, and the official version was released in March this year. Okay, so what are the main WorkManager entities? We have the worker, the WorkRequest, and the WorkManager. The worker is responsible to create the task. I mean, what we want to achieve with that worker. The WorkRequest is responsible to specify what kind of task should be. I mean, if it's a one-time request or a periodic request. And the WorkManager is responsible to hand off the task to the system. What's happening behind the scenes? What is the internal mechanism of the WorkManager? Behind the scenes, let's say we want to create a worker, and at that moment, the WorkManager will check to see what is the current API version. If we don't have API 23+, it will use the job scheduler implementation. If we have, it will check if we have Google Play services. If we don't have Google Play services, it will use Alarm Manager and Broadcast Receivers. And if we have Google Play services, it will use Firebase Job Dispatcher. So actually, WorkManager is more like a wrapper on these background processing solutions. So all the work that we should be done by us is done by the WorkManager for us. Let's take a closer look on the worker. We have a do-work method, and inside of it, we need to specify what is the task that should be done, and we return a result that could be a failure, a success, or a retry. In terms of code, we need to extend this abstract class, the worker class, and we need to define the function doWork. And inside of that, I call another function, load data, and that function is responsible to synchronize the data between the app and the server. And we return a success result. An important thing to mention here is that the doWork function runs synchronously on a background thread. WorkRequest. When we create a worker, we need to decide if it's a periodic one or not. If it's not a periodic one, we will use one-time work request. If it is a periodic one, we will use periodic work request. In terms of code, we will use some builders. So one-time work request for builder and periodic work request builder for the periodic one. For the periodic one, it's also important to specify the interval, in our case, 1 hour. So one-time work request, it is used for non-repeating work. It could have an initial delay, and it also could be chain. Periodic work request is used for repeating task. The minimum repeat interval that can be defined is 50 minutes, and it's extended from the job scheduler API. It cannot have an initial delay, and also it cannot be chained. Another important thing to mention here is that we are not able to be sure about the moment when the task will be executed, because it will be somehow determined by the OS battery optimizations. Another thing that we could define by using a periodic work request is to use the flex interval. So in this case, we have again a periodic request builder, and we have a repeating interval 8 hours and a flex interval 50 minutes, which so the work will run somehow within this period of time after the repeating interval. Okay, so we define our tasks. We specify what kind of task should be done, or it could be a one-time request or a periodic work request. And sometimes maybe we are interested to run our tasks in some specific conditions. In WorkManager, we have this possibility by using constraints. And these constraints are related to the network connectivity, are related to the battery level, or on the device storage, or we could also check if the device is idle. And also we could check if our device is charging right now. For the network type, it's an enum, and it has 5 values. So we will be able to check if the device is connected or not to a network, or to decide to know if the device is connected to an metered or unmetered network connection, or if it's important for us that our task should be run when the device is not connected to the roaming. In order to define the constraints, we will use Constraints Builder, and to apply those constraints to our request, we use the setConstraints method. Okay, so we defined the constraints, and for our case, when we want to synchronize the data between the app and the server, let's say that we want to synchronize the data only for the logged in user. And we would like to send the ID of the user to the task, and after that get some output. By using WorkManager, we are able to have inputs and outputs, and we use the data and Data.Builder classes, and we should think about them more like a key value set. So it's important to make sure that we don't save more than 10 kilobytes using those inputs and outputs, because if we'll try to save more than that, we will get an illegal state exception. And in this case, we have the possibility to use primitives and strings, and we have Boolean, double, float, in, long, and string from Java, primitive and strings, and we also are able to define some arrays for them. In order to apply this input, we use the method setInputData, and in order to, if we use KTX, we could use workDataOf to define the input value. Each task has a unique identifier. That identifier is created from the WorkManager and is not a human-readable code. So this is why sometimes it's important to tag our work and to be able to get that work using a specific name. We are able to do that by using the add tag method, and an important thing to mention is that a task could have many tags. Okay, so we saw that we have that unique identifier, we have the tags, and also we could define a unique work. I mean, a name that will not be used for many tasks. It will be used only for one. And we could get a unique work sequence or a unique work chain. And here we need to specify the name, and we have also an existing work policy. What is this existing work policy? We have the possibility to keep, replace, or append the task. In the case of keep, if the task doesn't exist, it will be in queue. If it already exists, it will be kept in the track. If we use replace, the oldest task will be cancelled and deleted and replace it with a new one, and the append will just append the new work if it not exist already. Keep, replace, and append is part of the existing work policy in enum, and existing periodic work policy contains only keep and replace. Okay. Maybe our task should be run at a specific time, or maybe if our task is not successful, I mean we have some issues during the execution, we would like to retry. And in this case, we have the BackoffPolicy enum, and this indicates that the WorkManager should increase the backoff time exponentially or linearly. And for one-time work request, we are able to set an initial delay. And to set up the backoff delay and policy, we'll use the method setBackoffCriteria. Work status. So we defined the task, we defined the type of the task, we started the tasks, and right now we want to know what is the status of our tasks. In order to do that, we are able to get the status using that unique ID, using the state enum, which has blocked, cancelled, in queue, failed, running, and succeeded, using the input-output data or the tags. If we want to get the status of a task using the unique ID, we have get status by ID or get status by ID live data. If we want by tag, we have statuses by tag and statuses by tag live data, and the same idea for unique name. So what we saw in that slide, in the previous slide, is that we are able to get the status of a work using the live data component. So we are able to observe the status of each task by using those methods. And for example, for the ID one, we get a live data of work status. And for tag and for unique name, we will get live data of list of work status. Okay, right now let's see how does it look a happy path for one-time work request. So first of all, the work is blocked because maybe we have an initial delay and it waits for it. And after that, it's enqueued. And after it's enqueued, maybe it waits some constraints to be achieved, to be met. And after those constraints are met, the running state appears, and because we are on the happy path, the result will be succeeded. An unhappy path for one-time work contains for sure the initial setup, and in the case that it runs and something doesn't work, and it has results .retry as a return type for do work method, it will continue to retry to do that task. If we get a failure, it will go to the failed status, and if the work is cancelled, we will go to the cancelled status. An unhappy path for a periodic work, it looks a little bit different because the periodic work will continue to run, and so we will not get a final state on the succeeded side. So the task will continue to run and retry. So in the case we have success, and if we have a failure, it will go to the failed, and if it's cancelled, it will go to the cancelled state. Now let's take a closer look on the WorkManager. We have some main methods: enqueue, cancel, begin with, and begin unique work. Let's say that we want to change some tasks. Let's say we have 3 tasks, and for the first task we have an input and we get an output. The output of task 1 will become the input for task 2. And the output for task 2 will become the input for the task 3, and so on. So what's happening here? Outputs are inputs to child tasks. In terms of code, that chain of tasks could be written like this. So we get an instance of our WorkManager and begin with the task 1, then continue with task 2 and 3. An important thing to mention here is that begin with and then return a work continuation object. Okay, let's take another scenario. We have task 1 and task 2 that works in parallel, and the output of those 2 tasks will represent actually the input for task number 3. In terms of code, we will use almost the same approach. The difference is that for begin with, we will use list of task 1 and 2. So there we will have a parallel execution, and after that we will continue with the task 3. In the same situation like previously, we get a work continuation for those methods. A different scenario could be to have more like a graph of tasks. So we have 2 different chains, and the result of those 2 chains will represent the input for the task number 5. So we will need to define those 2 chains, the left one for task 1 and task 2, and the right one for task 3 and task 4. And the result chain will represent also a combination of the result of the two other chains. And we will use the combine method from work continuation. And finally, we hand off the task to the system. Okay, so we changed the task, but you saw that we had those inputs. And it's important to know how those inputs are merged. In order to do that, we will use the input merger class. This is an abstract class, and it has an abstract method merge. And by default, WorkManager offers 2 implementations: ArrayCreatinginput Merger and overwriting input merger. Overwriting input merger is the default one. Let's check what's happening behind the scenes for the array creating input merger. So let's say that we have two tasks, green and pink. We have key values, and for the first one we have user ID and name, int and string, and for the second one we have user ID, name and token, int and two strings. What happens when we apply this strategy is that we get a result that will combine the other two key values from the other two tasks and create some arrays. So for the user ID, creates an array of integers, of ints. For the name, it will create an array of strings. And for the token, it will create a one size array of strings. Okay, what happens if we change the user ID type? Instead of int, we have a string. We'll get an exception, because in this moment we try to create an array of ints and string. So we have pollution. So this thing is not possible. Let's see what's happening when we use overwriting input merger. We have the same scenario, two tasks. We have the green and the pink one. We have user ID, name, and points for the first one, and user ID, name, and token for the second one. The user ID for the first one is an int, and for the second one is a string. First of all, it's for the result, for the output of those two tasks, first of all, we make a copy of the first task. So we get the user ID, the name, and the points. Until now, everything is okay. And after that, it goes to the second task and starts to override the values. And it doesn't care the fact that the user ID in the second task is a string. Just override the value and that's it. For the name, we'll do the same thing. It was previously Android Pie and right now it's Android Q. It will keep the points from the first task and the token from the second task. In order to apply the strategy in terms of merging the values, we use the setInputMerger method, and in this case we use the ArrayCreatinginput Merger class. Okay, to send the task to the system, we use the enqueue method. But what happens if we want to cancel the work? In this case, we have many options. If we want to cancel all the tasks, we have cancel all work. If we want to cancel a task only by using the tag, we have cancel all work by tag. And the same thing for cancel by unique name or by ID. Trading options. There are four main options right now implemented in WorkManager, but we are also able to create our own. Let's see first of all what's happening with the trading in WorkManager. So we have the work request. This work request is enqueue, and we have inside an internal task executor that will take this task and will keep it in a database. So everything is saved in a local database. They use Room, and this database is able to make sure that our task will run even if our system will restart. After a period of time, our constraints are met, and we have a worker factory that will create a worker, and that worker will be executed by an executor. The executor is already implemented in the WorkManager. So this is how the things are working in the WorkManager regarding the trading strategy. I already mentioned that everything that is related to the task that should be created by the WorkManager, all the information about those tasks is saved in a local database. So for my code, I got this database file, which has, in my case, 7 tables and 5 indices. And like you also see, we have tables for work name, for WorkSpec, work tag, and so on. And if we take a closer look on the WorkSpec table, we will get there more details about the state, about the input, output, initial delay, and constraints that are applied for each task. So this is how they keep the track of each task. So for our worker, let's go back to the trading idea, we have the do work, which is called on a background thread synchronously. And if we want to stop the work, onStop is called. We could overriden, or we could call the worker is stopped in order to release the memory that it's used. If we use coroutines, and I know that all the Android developers are right now a big fan of coroutines, they offer the coroutine worker. So instead of extending worker, we will extend the coroutine worker, and do work will be a suspending function. If we want to cancel to stop the work, this will be done automatically. If you are using Eric's Java 2, we have Eric's worker, so we'll extend the Eric's worker class, and instead of do work, we have create work, and returns a single of result. Again, the process when we want to stop the work is done automatically. And finally, let's talk a little bit about Listenable Worker. Listenable Worker is an abstract class, and it has an abstract method startWork. This Listenable Worker is taken from the Guava library, but if we want to use it in our code, we have a dedicated artifactory that should be included in a Gradle file. Actually, the worker, the Coroutine Worker, and the Eric's worker are implementations of this class. So Listenable Worker, it's only responsible to let us know when the work should start or stop. And when the work starts, that thing is somehow invoked on the main thread, and we go to the background thread manually. If we want to stop the work, we need to use a callback to future adapter in order to add a cancellation listener. Okay, so let's make a recap. We discovered that actually WorkManager is more a wrapper on the existing background processing solutions, and it writes all the code for us, and so we will spend less time in order to do this kind of stuff. We are able to create one-time or periodic work requests. We are able to chain those tasks, and we are able to identify our tasks by using the unique ID, the tag, or the unique name. We are also able to define some constraints when our task should be run. We are able to delay the task or to define a retry policy. We could use also input and output data and merge them, and we saw that we have two possibilities right now. And we are also able to use the existing threading options. As resources, I recommend the documentation, the official one, and there are some great presentations from Google I/O 2018 and from Android Dev Summit. They are on YouTube. Merci beaucoup. We have time for questions? Okay. I know that the party is coming, so I don't want to be an impediment for you. Questions?
Hi.
Please, yes.
Thank you for your presentation. I wonder how we should test the code where we are using WorkManager. Is there some library
for testing?
For supporting testing?
Yes, they offer an interface test driver, and they also have some helpers that could be used in order to test the implementation. So they have a dedicated library, and it should be included in the Gradle file. Other questions?
Hi. So my question is about the database that you showed. Is it like a global database for all the apps, or is it counted on the app memory? What happens
if per app? Yes.
Okay. What happens if the user clears all the data of the application? Will the jobs be cleaned, or will that impact in a way the predictability of execution of the work?
Okay, so that database, I access it from the device explorer from Android Studio, and yes, each app has its own database for those workers. So if you clean up the database, the WorkManager will not be able to know what should be done next, because that's the idea of persisting the data there. And they are using Roam, I saw in the implementation. Okay, thank you. It was a good answer for you. Okay, thank you. Any other questions? Okay then. Thank you very much and enjoy the party.